In section 8.5, we're going to be testing claims about means when we don't know the standard deviation of the population, sigma. If you think back to confidence intervals, when we didn't know sigma, we had to use a t-score instead of a z-score, and that's the same situation for hypothesis tests. So in this section, we're going to be working with a t-distribution instead of a normal distribution that we have been using. And again, the reason that we do this is because we don't know the standard deviation of the population, sigma. So in part A, it's asking us to find the critical value for a hypothesis test with a sample size of 18, alpha equals 10%, and it's a two-tailed test. So to refresh on t-distributions, we always have degrees of freedom, and that's given by the sample size minus 1. So in this case, we're going to have 17 degrees of freedom, one less that sample size of 18. And now if you look over here, you see confidence intervals up top. Underneath that, we have one tail and two tails. This test, we're talking about a two-tailed test, find 10%, and then we're just going to trace it down. Critical value 1.740. Since it's two-tailed, we want the positive and the negative 1.740. In part B, it says n equals 9, so we have 8 degrees of freedom. Okay, this is a right-tailed test, so it's one-tailed. We want 0.025, all on that right tail. The right tail is the positive one. If it was a left tail, it would be the negative of this value. Since it's right tail, just t equals 2.306. We also want to be able to use a test statistic to obtain a p-value. So in part A, we have t equals 1.562. This is our test statistic, just like we found the z-score in the last two sections. It tells us we have a sample size of 17, which means we have 16 degrees of freedom. And let's look at the numbers on this line here. Okay, so the smallest number on that line is 1.337. The largest one is 2.921. These numbers up here, okay, it's a two-tailed test, are the p-values that would go with that number. So if we had a p-value of exactly 1.337, for example, that would equate to a p-value of 20%. Okay, if we had a test statistic of 2.921, that would be a p-value of 0.01. So we have an actual test statistic of 1.562. The question is, where would it go on that line with 16 degrees of freedom? Okay, it would end up in between these first two because it's bigger than 1.337 and it's smaller than 1.746. Okay, which means it's going to be in between those two percentages. So our p-value is somewhere in that range, larger than 10%, but less than 20%. Okay, same thing for part B. T equals negative 1.267, n equals 8. In this case, we have 7 degrees of freedom. We're on this line here. Okay, since it's a left-tailed test, just imagine all of these are negative. This particular test statistic would end up to the left of all of them. Okay, 1.2 is smaller than 1.4. It's smaller than all of these on this line. This is a one-tailed test this time, which means our p-value is larger than 10% because these are getting bigger as they go to the left there. All right, let's do an actual example. We have a survey of 15 large US cities. We find that the average commute time one way is 25.4 minutes. There's a local politician. He feels that the commute time in his city is less. He randomly selects 25 commuters, finds the average is 22.1 minutes with a standard deviation of 5.3. Is he correct? So first off, we're going to define our parameter. The parameter is, okay, it's a mu again, because we're talking about quantitative data. This is based on numbers, not categorical questions. And mu represents the true mean one-way commute time in US cities. Hypothesis, the actual mean is 25.4. Politician says that it's less than that, so alternative is mu is less than 25.4. Critical value. So this is a left-tailed test. We have an alpha level of 10%, one tail, 10%, t equals negative 1.318. It's negative because it's left tail. It's on the left side of that curve where all the numbers are negative. What's the standard deviation? So standard deviation is given by S over radical N. This is the standard deviation of the sample and not the population. So this is based on just 25 commuters. Those 25 commuters have an average of 22.1, standard deviation of 5.3. S over radical N gives us 1.06 for the standard deviation of this distribution. Test statistic is a t-score because we don't have the standard deviation of the population, but we find it the same way as we would find a z-score. So we have a mean of 25.4. That's based on that null hypothesis being true. How unlikely would it be for us to sample 25 commuters and find that they have an average commute time of 22.1 minutes or less? So 22.1 minus that mean, divide by the standard deviation, which we found on the previous slide, and we get that t-score. So again, with 24 degrees of freedom, where would this go on this line here? It would be way out on this side, which means our p-value is less than that number. Okay, it's getting smaller as we go to the right. P-value is less than 0.005. Now that's a really small p-value. It's less than 1/2 of 1%. And what that's telling us is if our null hypothesis is true, and if drivers' commute times average at 25.4 minutes one way, if we took a sample, we would expect it to be fairly close to that 25.4 minutes. Instead, we took a sample of 25 and we got 22.1. That's far enough away where it would pretty much never happen by chance. Okay, it would happen like less than 1 out of every 200 times, according to that probability. So the most plausible explanation is that initial assumption is incorrect. The mean is not actually 25.4 minutes. It's less than that. So we're going to reject the null hypothesis because that p-value is small. Either we witness something really, really unlikely to happen, or this is incorrect. And the most likely explanation is that's incorrect. So anytime we have a small p-value, we reject the null hypothesis. It's smaller than that alpha level. The conclusion, our last sentence, is always about the alternative. When we reject, there's always sufficient evidence to suggest that the alternative is true. So in this case, there's sufficient evidence to suggest that the mean one-way commute time is less than 25.4 minutes. That was the p-value method. Now we're going to do another one with the traditional method. Here we have information on robbery victims and their average age. The hypothesis is that their average age is 63.5 years. We have a sample of 20 recent victims. They had an average age of 64.1 years, standard deviation of 1.9. Okay, is that enough evidence to suggest that the average age is higher than we initially believed? Parameter, mu is going to represent the true mean age of robbery victims. Null hypothesis, we're assuming that it's 63.5, and we want to see, does this sample of 20, resulting in an average of 64.1, give us evidence that it's actually higher than that 63.5? Alternative is mu is greater than 63.5. Standard deviation, S over radical n. So the standard deviation for all 20 of these victims was 1.9 years, but the standard deviation of our sample is that divided by radical 20. We get 0.425. Test statistic is based on the null hypothesis being true. So if the average age actually is 63.5, how unlikely would it be for us to talk to 20 people and find an average of 64.1 or more? T-score is 1.41. Critical value. Here we have an alpha of 0.01. Okay, we have a one-tailed test, it's right-tailed. And we had 20 victims, which gives us 19 degrees of freedom. So we go on that line. We're looking for the critical value for 1% on one-tailed, 2.539. Now with the traditional method, we're just going to cut out the p-value. So we have this critical value that we just found, 2.539. Anything greater than that for a test statistic means we're going to reject the null hypothesis. The test statistic, which we found 2 slides ago, was 1.41. Okay, 0 is right in the middle, which means this is just a little over halfway to that shaded region. The important thing to notice is that's not in the shaded region. We would have to be larger than 2.539 to be in that shaded region. So because it's not in the shaded region, this average that we saw in our sample was not far enough away for us to say this is untrue. Okay, so in this case, we're going to fail to reject the null hypothesis. This average is in line with that. We would expect to see averages in that low 64 range if the mean was actually 63.5 years, just based on the fact that samples vary. Okay, when we fail to reject, like we did here, We always say that we don't have enough evidence to suggest that alternative is true. This last sentence is always about the alternative hypothesis. So in this case, there's insufficient evidence to suggest that the mean age of robbery victims is above 63.5 years.